In fact, gravity is supposed to be uh, uh, gravity is supposed to be absorbed in the very geometry of space and time. The gravitation attraction, if you like, is just a manifestation of the curved nature of space and time. Gravitational waves are just ripples on the curvature of space and time. So gravity is completely subsumed by the geometry of space-time and its manifestations of its various properties. If this is the case, then a quantum theory of gravity also should be a quantum theory of space-time geometry. So
nice.
quantum...
Your time. How are you doing this morning?
I'm well, thank you.
Excellent. I once again, I appreciate it very much. Thank you for your time. And if you don't mind, just for those that don't know, I was going to briefly kind of go over some of an introduction for you that to kind of, for people that may not know your background. Dr. Abhay Ashtekar, he's currently the Evan Pugh Professor of Physics at Penn State, where he currently holds the Eberly Chair. And his scientific work focuses on the theoretical aspects of general relativity, cosmology, and quantum gravity, initiating loop quantum gravity by introducing new variables to Einstein's equations. He has played a leadership role in the development theory of quantum theory of Riemannian geometry, and also additionally holds an amalgamation of accolades that are very, very impressive, among those being National Academy of Science, a fellow of the American Association for Advancement of Science, and also the highest honor in the field of gravitation, the Einstein Prize of the American Physical Society. In addition to that, I know that you have attended University of Texas at Austin at some point in your career. So that's kind of a common ground between us. Not that I've attended the university, but I've been a longtime fan of their programs and sports. So
you were living in Austin for a while.
Correct. Yes, sir.
Yeah.
Yes, sir. Still very close to there. So I find some common ground with you there that Austin's a really neat place. And additionally, I noticed that you are a fan of the Bhagavad Gita, which is a very, very impactful text to me. And so it was very neat to come across that fact about yourself, because when I discovered that text, the Bhagavad Gita, it was enormously important to me. And it still is. And so I think that's really neat. So after all of that, thank you again for joining me, and I appreciate your time. And to start off, what I was attempting to kind of do is, and what I've been trying to do is essentially come up with an idea, looking into the theory, looking into consciousness, and attempting to come up with some type of storyline as to maybe how a subjective experience can merge with physical reality, as you call it, the inner and the outer world, and where that bridge exists, and how they subsume each other, and if they even do, I guess. And so that starts ultimately with, to me, it seems like space and time, which is a difficult concept for a lot of people. I know looking at space and time as space time as a different entity altogether creates this visual that people have, that it's a interlacing lattice structure of space and time that involves mass and space, time, energy, and all of that into one. And that's a kind of what's called like a background dependent view, I believe. And so I kind of wanted to start off by just kind of going over what your view of a background dependent space-time looks like, what that means, and how that's being kind of gotten away from, and what that means.
All right. So I think most people are really familiar with Newton's idea of space and time. That is what we are taught in high school, and we intuitively use in our everyday life. So the Newton's views of space and time, which was just postulated to give order to the observations in astronomy that people had been making. In this view, space is absolute three-dimensional continuum, and time is an absolute one-dimensional continuum, and they just march along. In other words, it's really fixed once and for all, and time just marches along in a linear fashion, independent of anything else. So this is like a stage which is just set beforehand, and it has nothing to do with the physical entities that exist. So it is like a stage or an arena on which all the actions happen. The planets move, the you and I move, we've got tables and chairs, all these things are really sitting in this space-time, which is inert. And this is the view that really lasted for a very long time. I mean, we think of time as being absolute. You know, if I snap two fingers like that, then there's a time interval in between them, and we think of that time interval as being the same, no matter who measures it, and so on. So time is absolute and space is absolute. This view really lasted until the 20th century, and were shattered by Einstein's theories of relativity. So I'll be very brief here. Einstein really did this in two stages. The first was called special theory of relativity, and the second is called the general theory of relativity. And it is a general theory of relativity space-time view that is what is used in contemporary physics. So in this point of view, I mean, the two are not incompatible. General relativity space-time point of view is a generalization of that of special relativity and of Newtonian, the space-time point of view. So in this view, the idea is that space-time is not an inert entity. It is not a stage on which things happen, but space-time, or geometry of space-time more precisely, is really a physical entity, you know, just like you and me, just like this table, just like stars and everything else. And the matter, like heavy bodies, they can bend the geometry of space and time. So they can bend space and time. They can cause curvature in the geometry, as one says in a technical term. And conversely, this bent space-time, this curved space-time dictates how matter moves, so how the planet moves, but also how light propagates in this case. So everything is really dictated by this interplay between space-time geometry and matter. So this is really the fundamental point of view. And then in this view, there is no stage, there is no fixed space and time in the background on which things happen. And therefore it is called background independent, as opposed to the background dependent one, which was for Newtonian theory, in which, you know, there is given something, there is a background space-time that is sitting there all the time. In here, there is no background space-time, as technically one says. There is no kinematical structure. There is no, everything is dynamic. Everything interacts with everything else, including the geometry of space-time itself. So what background independence entails, that is what Einstein taught us, and that is perhaps the deepest lesson of general relativity, is that space-time, or geometry of space-time, is also a physical entity, very much like matter. And the two are intertwined with each other via specific equations, which were written down by Einstein. They are called Einstein's equations of general relativity. If you see my screen on the very top line, that is Einstein's equation of general relativity up here. The second one is Einstein's photoelectric effect, and the third is the special relativity equation, E equal to mc squared. This, by the way, is Einstein holding this plaque, and this is a really big statue of Einstein in front of the National Academy of Sciences in Washington.
That's really neat. I like that. That's a really cool backdrop too. And to kind of restate what you were saying, to see if I'm grasping it just quickly, is I think generally it's assumed kind of that, like you had said, that this background, or so to speak, of space-time is the arena. And as matter and motion and time unfold, it's somewhat like things, it's fundamental or a precursor to everything else. And so I think the main thing when the inner world is trying to be united with the outer world is there's that view of materialism that quantities and qualities, or quantities of things, give rise to qualities of experience, and maybe to presume that the space-time may not be this fundamental arena that births everything else, has deep implications potentially for what the inner world would look like, as far as making that bridge that we were talking about between the two. And I just wanted to kind of see is if looking at space-time like this, is it kind of has implications for the fact that maybe it's not the most fundamental overall.
Yes and no. I mean, in the sense that um, I had to back up a little bit because I have
Sorry.
to sort of put it in the context of here. Um, Really, there are kind of, I mean, what we have is our perceptions, our experiences, and then we try to make sense of this and of these perceptions. And it seems to me that there are really two hypotheses that are made. And these hypotheses, I think practitioners don't often realize, but if you when pushed, they would agree that these are hypotheses. The first hypothesis, possibly, is that what is out there, there is an external world that exists, and I am part of it. And I am trying to make sense of this external world. And that is the hypothesis that underlies the outer world or the explorations of science. It is assumed, it's taken for granted that there is an outer world and I'm making sense of it. There is an alternative hypothesis, which is that, well, really, all I have is my perceptions. And therefore, what I've created is a certain model to explain, or several hierarchy of models to explain that outside my perceptions. And therefore, the external world is a model that I have really created. And I have created it to explain my perceptions. So in some sense, one might say that my perceptions or my consciousness, although we'll come back to that because the word consciousness is used in very different senses by different people.
Certainly.
My consciousness is really kind of fundamental. And neither of them is really, provable, or at least so far. And in fact, you had this conversation with, I think, Dr. Hoffman, is that correct?
Yeah.
And he is very candid about it, saying that he is hypothesizing that the consciousness is there and is fundamental. Okay, so there are these two alternate views of quote unquote accounting for our perceptions, putting order in our perceptions to enable us to function. And the statement is that one of them has given rise to exploration of the external world, or what is generally called as science, and the other to the exploration of the inner world. Now, there's an overlap between them, and constructing the bridge between them is a big point, and I think is a big, to me, the biggest issue. I don't think that that this is regarded as a fundamental thing, because most practitioners are either on one camp or the other. And therefore there is not enough dialogue between them. Now, returning to space-time. So what I explained before is the best view of space-time we have today, coming from Einstein, from the external world perspective. And it is true that there are some elements in here which say that space-time itself is dynamical, it's not given, it's not God-given, it's not sitting there, it's not forever, etc. That rings a resonance or a bell with the views of the inner world, in which the space-time structure is considered to be a model which is very useful, etc. But I don't want to say that one is the same as the other, one implies the other, or anything like that. Because in general relativity, as you see, there is explicit equation which tells you what space-time structure is like and what it does. That is not there in the inner world. In the inner world, one doesn't account for the space-time in this particular way. They just, in other words, there are about 12 different notions of time, and one of them is psychological time, and the inner world often focuses just on the psychological time rather than measured physical time.
No, thank you for reiterating that. For I think, like you were just saying, something interesting is the idea that mathematical equations oftentimes have to be accompanied by a theoretical model, a model of some sort, which is kind of where geometry meets algebra, so to speak, in my limited understanding. And it's critical that model is understood to be a representation and maybe not static and stoic in its existence. And so it's interesting with mathematics, and just like Gödel's incompleteness theorem, I always find kind of interesting. It's the notion that there's always something kind of missing between the mathematical background and a piece that completes that incompleteness part of it. But to move on from that, I guess kind of models become very important in when we're talking about the very large Newtonian general relativity. But then when it gets to the very small, oftentimes it's fun to explicate the notion that these two things are hard to combine, that of quantum mechanics and general relativity. So I was going to ask you, as your work and a pioneer, so to speak, of this work, what can we learn from loop quantum gravity, and what is your attempt with that and to do with that in making these two kind of come together? If I know it's a large question, but if you don't mind, kind of explaining that a little bit.
So yeah, I'll just say it's a large question, so I'll divide it into some
Thank you.
and then we can explain it.
Thank you.
And then go into it. And at the end of any part, if you have would like more clarifications, just ask.
Thank you.
I will try to stop at several places up here. Okay, so as you said, general relativity is a theory that Einstein discovered, and it is the best theory that we have today of both structure of space and time and of gravitation. And his predictions, this theory, by the way, was the final equations were written down by Einstein in 1915. So this theory has been with us for over a century, 107 years now. And it has been subject to some of the most severe observational tests. And the most recent of them has to do with black holes, mergers of black holes, collisions of black holes, and also collisions of objects called neutron stars, which are fascinating. And every time this general relativity has triumphed, it has been applied to the universe as a whole. So far, we don't find any deviation from general relativity as a classical theory of gravity. So observations are completely consistent with general relativity. Interestingly, quantum mechanics was discovered about the same time. And although it is not often kind of recognized, Einstein was also one of the founders of quantum mechanics. And the second equation on the screen, this is Einstein's equation, basically h nu is the energy up here. And this is a photoelectric effect. And the photoelectric effect is the voltage, this electric charge, and the h is the Planck's constant, nu is the frequency of the photon, and a is a potential that the light has to overcome to be emitted. Okay, so photoelectric effect is the one that for which Einstein actually got the Nobel Prize. So it really is quantum mechanics, and of course there are many quantum mechanics, unlike general relativity, had many important key players. And now quantum mechanics really is applicable, or it comes on its own. It's applicable. I should say it comes on its own in the micro domain, as you say, where general relativity comes on its own in the macroscopic world, in the cosmological world, in astrophysical world, and so on. Now, the interesting thing is that each of these lays a claim of how nature, that is to say, the outer world, has to be described. General relativity says that, well, everything is really an interplay between the geometry of space-time and various fields. And these are technically called classical fields. So these are, either numbers or vectors or tensors at each point in space-time. And then their behavior is dictated by certain differential equations, how they propagate, how any source creates these fields, and so on. So general relativity says that there is supposed to be, ultimately, space-time is going to be represented by a continuum called a manifold, technically. And that on that continuum, there are all these fields, and then there are, at each point of this manifold, there is what is called light cone. So that dictates the notion of causality, and all the causal signals can be propagated. In other words, you can only affect that part of space-time by waving my hand up here. I can only affect what happens to the future and not to the past. and that is captured in the idea of a light cone, that what is contained in the light cone is really are the events in space-time that can be influenced by any given disturbance at a given point at which we're drawing the light cone. And so now quantum mechanics, on the other hand, has its own claim as to how nature should be described. And that claim says that no, I mean, the fundamental theory is really basic constituents. You have to describe by things to be this constituents. And quantum mechanics, by the way, just accepts space-time as given. So much of quantum mechanics even assumes Newtonian space-time, or what is called non-relativistic space-time, which is incorrect. Some of it does do special relativistic space-time, and some of it also does general relativistic space-time. So, but it assumes a space-time in the background. It just presumes a model of space and time that is given to you. And depending on the context, in the subatomic world, typically what happens in the dynamical nature of the geometry of space and time is ignored, and one just assumes that space-time is inert, is living there forever. So there is a tension, because one is assumed, in one case, the space-time is just, most of the time, space-time is just given to us and is living there. But in any case, what is quantum mechanical is really properties of matter. So there are quantum field theories which are the best descriptions of the matter that we have, the elementary particles and the forces that we have today. And that is the best description that we have. That comes from quantum mechanics. But quantum mechanics, on the other hand, says no, the world is not described by this differential equations and tensor and fields, scalar fields, which take precise values at a point, vector fields, which is a little vector pointing in some direction at a point, etc., etc., and tensor fields like the ones that are on the screen, which are written up here. So the quantum mechanics is not like that at all. It is really, there's a completely different mathematical description. It is not geometrical like here. Here the description is geometrical in terms of geometry of space-time, geometry of the way the fields evolve or propagate in the space-time, etc. In quantum mechanics, the description is much more algebraic. Technically, one says there is a Hilbert space of quantum states, there are operators, and then the most importantly, the predictions are probabilistic. I do not know what happens in any given experiment. Typically, if I make a measurement, you have to make a large number of experiments, and then I can provide you with a probability distribution, and you will verify that this probability distribution is actually realized at the end of this large number of experiments. So the key point is that the two are claiming that they own the whole territory, that they actually give you the language to describe all of physics. And these two languages are very, very different. The syntax is very different. It is really, and therefore the concepts are very different. And so then when we look at quantum theory of gravity itself, then there's a collision. Because on the one hand, general relativity says it should be described in a particular way, and quantum mechanics says it should be described some other way. And the question is about how do we unify principles of this quantum mechanics and general relativity. So this has been the question for the longest time.
Yeah, understood. Yeah, thinking on the notion of quantum mechanics, it's often in just fields in general. It's those are hard to conceptualize too. It's electromagnetism and Maxwell's equations. They seem to have a similar nature to them. I'm not a mathematician by any means, but the inverse square law that's generally referred to in gravity, it seems to have a relation to the Maxwell's equations to some extent to describe the interactions of electromagnetism. I came across this recently and just found it to be somewhat unique because it seems like the fields of electromagnetism have some parallels to what occurs on the grander, larger scale. And then quantum mechanics is also fundamentally what I thought is kind of supposed to describe the interactions of electromagnetism. So understanding what you just said about the integration of these two being, both of them thinking they're the supreme theory and trying to unify them is the goal of your work and the work of many, I assume. But as far as electromagnetism and the integration of that with gravity, is there anything there with Maxwell's equations that you see that prompted this kind of that's unique about that? Comment how similar it really is to the interactions of distance between masses.
So the force in the case and sense of Newtonian mechanics, the force between two charges obeys the universe square law. In other words, the force is proportional to the product of the charges divided by square of the distance between them. And it's also true that the force between two masses is proportional to the product of the masses divided by the square of the distance between the two. And it is correct to say that that is how we began our explorations of both gravity, and actually gravity came first through Newton, and electromagnetism. And then one saw that there is exactly the same law really is true at this simplest level. But this really is a very simplest level. The analogy doesn't persist after that. There are big differences between the two. I mean, the most obvious difference is that gravity acts on everything. Everything is a mass. Gravity or mass is equivalent to energy, as the last equation here says, and therefore everything gravitates, including gravity itself, actually. Whereas that is not true with the electromagnetism. Electromagnetism, only charged particles feel the electromagnetic force. Neutral particles don't feel electromagnetic force at all. So there is a big difference between the two. And there is also a huge difference that there's in some loose way similar, but conceptually and technically, there's a huge difference between the Maxwell's equations and Einstein's equations, which are on the top here. There are common features. Mathematically, they're both hyperbolic equations, and therefore, if you give me a source, I can tell you what the propagation is. There are waves. What you talked about was the static electric and static gravitational force about the universe square law. But there are also electromagnetic waves, and that's how we are communicating right now.
Yeah. And the reason that it struck me as interesting was just because looking at the E equals MC squared equation, it seems to me like if you do a layman's dimensional analysis of it, it breaks down to the speed of light and time kind of irreducible to a certain extent. And lambda nu the frequency times wavelength, as is written up above that, that is equivalent to the speed of light from what I understood, like once you break it down. And so if the wavelength times frequency, speed of light, but speed of light's also that fundamental constant that equals energy when combined with a massive body. It seems interesting when you get to that point, what the relationship really is between frequency and wavelength, light and mass, where it kind of just where it emerges from. It seems like there's obviously a relationship between energy and mass, and maybe the distinction is hard for someone like me to conceptualize, because if they're equivalent, it's like without that constant speed of light, they would be kind of inertial. They wouldn't be accelerating. And I know that seems to be one of the precursors to the idea of general relativity, is like adding acceleration to a mass at that point involves there must be bending of light by gravity. So I wanted to ask, I guess, how does gravity act on subatomic particles, and what is loop quantum gravity an attempt to describe that functionality or that relationship with geometry, so to speak, quantum geometry?
Right. So again, this was the first question that you had asked.
Sorry,
I just broke it down. I'm coming to that question. So we're trying to go in stages. So first of all, I told you about general relativity and quantum mechanics. Now to tell you why the problem of unification is so difficult, and then I'll tell you various attempts, and then what loop quantum gravity does. So the problem is difficult precisely because in Einstein's theory, as I just explained, the geometry of space and time is a physical entity. It is a dynamical entity. And the key thing that came out of general relativity is an astonishing fact that what Newton called as gravitational force is really an approximation. This is what we were talking about models beforehand. It was just a model, and if you take general relativity as being reality, which it is not, because it's also a model, but it's a more refined model. So what we have in science, this is not emphasized often enough, is really hierarchy of more and more refined models of the presumed reality. As I said, the outer world assumes that there is an external reality, and what we're trying to construct is more and more refined model which subsume the earlier and slightly cruder models. So general relativity is really subsumed that, and I subsumed Newtonian ideas up here. And what one is saying here is that the geometry of space and time is really a dynamical and physical entity, just like these tables and chairs around us or planets and everything. It can be acted upon, it acts back. Now, if I look at a table or chair, or even the screen that we are now looking at up here, it looks like a nice, smooth continuum. But you know experimentally that if you just put the screen under an electron microscope, you will see that it has an atomic structure. And the reason why it looks so smooth is because of an approximation. Namely, our eyes cannot focus on, do not have the resolution that is needed to see the atomic structure. We only average out, or as one says in physics very often, we only coarse grain.
Yeah.
And if you coarse grain the atomic structure, then you get this continuum of the screen that you are. So now, if in fact gravity is supposed to be absorbed in the very geometry of space and time. The gravitation attraction, if you like, is just a manifestation of the curved nature of space and time. Gravitational waves are just ripples on the curvature of space and time. So gravity is completely subsumed by the geometry of space-time and its manifestations of its various properties. If this is the case, then a quantum theory of gravity also should be a quantum theory of space-time geometry. So quantum theory of gravity should be also a quantum theory of geometry. In other words, just like the screen in front of us seems like a smooth continuum but has atomic structure, space around us seems like completely continuous and smooth, but that is just because we cannot probe it to sufficiently small scales. So the general consensus is that if you probed it at a sufficiently small scale, you will find that it is not a continuum, something else happens. And this scale at which these things happen is called the Planck length, which is about 10 to the minus 13, 10 to the minus 33 centimeters, which is really tiny. I mean, one doesn't realize how tiny it is, but it is really, for example, the proton, which is considered to be the minutest particle sitting in the nucleus of an atom, is about 20 orders of magnitude larger than the Planck length. So proton would be an absolutely astronomically huge object if you think of Planck length as being a centimeter, for example. It will be 10 to the 20 centimeters. It's really absolutely huge object up here, astronomical. So the idea up here is that at the microscopic level, at the Planck level, this continuum of space-time would break down and it should have some atomic structure. And now, if you don't have space-time in the background, we don't know how to do quantum mechanics. Because I was mentioning before, most of so-called non-relativistic quantum mechanics, in fact, assumes a very crude model of space-time, namely the one that was given to us by Newton 300 years ago, more than 300 years ago. The more sophisticated quantum field theories assume that model of space and time, which was given to us by special relativity. In both these cases, space and time is an arena. It's a stage on which things happen. It is fixed. And quantum mechanics, quantum things are happenings in this space-time. So there is a tension. I mean, how do you take ideas of quantum mechanics, like the wave functions, observables, which are represented by operators, the so-called eigenvalues of these operators, which is what is energies and angular momentum that is measured in laboratories and so on and so forth. So how do you extract all these things out of in a theory in which there is no space-time at all?
Yeah.
And that is a big challenge for quantum mechanics. So this is the second part of the answer.
Okay.
The first part was to say why, what is quantum mechanics, what is general relativity, and why there is a tension. And now, why is it so important? Or that each of them claims that they describe the whole universe. They give. On the other hand, well, every time this happens, there is usually a grander theory which subsumes both of them, and then we obtain in that grander theory. These are special cases. For example, in general relativity, there is a special limit in which you get Newtonian gravity, and there's another limit in which you get special relativity of Einstein. In special relativity, gravity is ignored. In Newtonian limit, the fact that light propagates at a finite speed is ignored. So you're got always a grander theory from which previous theories can come about. And what we're looking for quantum gravity is a grander theory which will subsume these two. Yeah. And then now, the second part, what I explained was why it is so difficult to combine the two. And to me, the main difficulty is really in the fact that continuum fixed space-time that is assumed in quantum mechanics disappears. And what we have to do is really talk about atoms of geometry of space-time itself. Again, as I said, the screen looks continuous and smooth, but it has atomic structure. So the very geometry of space-time, which in Einstein's theory is curved, is really exotic around black holes and so on, but it's still continuous. One doesn't worry about its atomic structure. And now what we're trying to do is to zero in and try to find out what its atomic structure is. So I'll stop here, and the third part, I will explain what is the ideas of loop quantum gravity to address this issue. But maybe you would like some clarification or something at this stage.
Sure.
So I'll stop.
No, I appreciate you breaking that down for me, because I know it was a large question. And I think I'm following you, and I think it's interesting to say, yeah, once you get to the quantum mechanical space, at least in my understanding too, is that there becomes this as I kind of noticed in this year's Nobel Prize for physics, which was the non-local interactions, those kinds of things that have always the spooky action at a distance, as is generally quoted, kind of puts quantum mechanics in that field where you have things happening quicker than the speed of light. And to me, that would, or that might be my misunderstanding, but it seems like that phenomena isn't necessarily easily described by general relativity, and quantum mechanics in this model doesn't presuppose it can't presuppose this background by which things interact, whether the geometry of space-time itself is giving rise to space and time as a construct. And so it's not this arena that it's unfolding on, and the dueling battle between the two is kind of there's got to be something, just like electricity and magnetism, electromagnetism came together, something of that nature you would want to see that is subservient, or these are subservient to a larger supervenient theory. But that being said, I know I quoted the idea of the chemistry of geometry that Wheeler put forward, and it's kind of what you're describing is when we talk about chemistry at the level we're talking about, these like when we put sugar in a glass of water and it dissolves, we understand that that's occurring because water's polar, sugar isn't, and then you have this kind of interaction at the molecular level. Geometry at the lower level interacting with itself is kind of how I interpret it. But I wanted to see with that, I know the chemistry of geometry thinking is kind of out of context by just using that one particular quote, but I do find it kind of a good way of kind of visualizing it. And so I guess I wanted to ask you about that and about the findings of this year's Nobel Prize, like how those non-local interactions, were they kind of some of the things that would lead physicists to question the general relativity as far as how it works at that level?
No, I don't think so.
Okay.
There is no causal propagation, which is faster than light. In these experiments or anything in quantum mechanics, there is no causal propagation between two events, which happens at a speed which is faster than light. It's much more subtle than that. So, but there's no contradiction with either special or general relativity and these findings.
Okay.
So you asked me about the chemistry of geometry.
Yeah.
Now this is intertwined with what loop quantum gravity is. So what I will do is, I began by answering your question about loop quantum gravity. I just finished the first two parts, namely why there is tension, and then secondly, why is the problem of unifying general relativity and quantum mechanics so difficult. And now I still have to explain what loop quantum gravity does. But we can take up what you said just now about Wheeler before that, and then I will tell you about what happens in loop quantum gravity.
Okay, thank you.
Yeah, so Wheeler was a kind of a visionary. In his younger days, he really did very, very deep contributions to nuclear physics, particularly with Niels Bohr, but also by himself. But then, in the later years of his life, he turned to general relativity. And he is single-handedly most important. Politically most important person, politics of science. Most influential person to make general relativity more mainstream, saying that it really has to do with the universe, and previously people were not taking general relativity as so seriously in physics and so on. Okay, but when it came to quantum gravity, and he also sort of started talking about quantum gravity coming from nuclear physics. He was quantum field theories first, then he got interested in general relativity, and he made many pioneering ideas and suggestions. But most of them were kind of qualitative and not in depth, developed in great detail. The idea of chemistry of geometry is really fascinating. And it somehow, in some ways, it grows out of ideas that were already present in Einstein's work, where Einstein was talking about unified field theories. But it's not the same idea, but it is along the same lines. So what Wheeler had in mind was the following. As you just mentioned, in chemistry, like the sugar and the water, for example, what happens is really at a fundamental physics level, what we have is atoms, and then these atoms get together, make molecules, and then of course these molecules is what was important for our biology, for the clothes you wear, and everything is all chemistry, dictated by chemistry up here. So in going from kind of more fundamental entity, which is an atom, to molecule, which is really much more complicated entity up here. So the idea was that at a fundamental level, what happens to molecules could be reduced to what happens to atoms. And it's absolutely true, because atoms get together, they make molecules. In practice, of course, it's very hard to go back to the basics to atoms all the time in this part, but conceptually it's true. That is a statement. So now, as I was just mentioning a few minutes ago, even if I looked at a proton, which we think of as being the really minutest particle because it is sitting in the center of the nucleus, in the nucleus of an atom, center of an atom up here, it is still 20 orders of magnitude larger than the Planck length. So Wheeler envisaged that interesting things will happen to geometry at the Planck length. So there will be fluctuations in the geometry. So this is pure geometry now. And now, if there are some fluctuations of one kind, then those fluctuations may come together. And then if they may come together, and then they may form a stable state of geometry. And this stable state would be perhaps acquire the meaning of an elementary particle, like a proton, for example, or a muon or something. I mean, the idea was that the elementary particles are like molecules, and atoms, the role of atoms is played by quantum fluctuation of geometry itself. So elementary particles themselves would be manifestations of geometry, just very complex configurations of geometry are interpreted as elementary particles because they take as it's convenient to think of them as an entity in their own right and manipulate them, understand their properties, just as it is convenient to think of H2O as a molecule by itself and understand its properties and what happens to it, rather than all the time breaking it into hydrogen or oxygen. And so this aggregate is important, but on the other hand, at a fundamental level, it has some constituents. Similarly, Wheeler thought that proton and neutrons, they are of course important, but they are not fundamental. And that the fundamental constituents may be tracked down to something which are purely geometrical nature, purely. So this is the idea, and he had this slightly more detailed ideas involving what he called geons, which are supposed to be these non-trivial topological configurations of gravity, which might be stable and so on. It turned out that many of those conjectures are not really correct mathematically. They are not borne out. And therefore, this idea of chemistry of geometry is really no longer pursued. Doesn't mean that it's wrong. It's completely, but it's no longer pursued. Just for your audience, it might be interesting to say some history of this a little bit,
sure,
going back to the 19th century, end of 19th century. So at that time, people had just started understanding what could be the atoms. So now I'm talking about atoms and not elementary particles, because people didn't know that atoms themselves have some other internal structure, right? They thought atom is really the indivisible thing, right, in those days. But at that time, they're spectral lines, and they could distinguish between elements. And they thought that each element had atoms, and those atoms were the irreducible building blocks. And then the question was, why are there so many atoms? Just like for Wheeler, the question was, why are there so many elementary particles? They can't be all fundamental. There must be something more basic, which is more fundamental. So in the olden days, people also thought that, why are there so many atoms? Is there some explanation? And then it is not well known, but it's really a fascinating piece of history that leading people like Maxwell, Lord Kelvin is who pushed this idea. Maxwell strongly supported it. They thought, in those days, people believed in ether, which we know now doesn't exist from special relativity and experiments that have been made. But in those days, people believed that there was ether, all-pervading medium in which light propagated, and the speed of light was constant with respect to this ether. What we call as speed of light is really with respect to the ether. This is not the case. Speed of light is constant in any frame, but in those days, that's what people believed. So there's supposed to be this ether, and idea was that maybe what happens, atoms are vortices in ether. So the idea was that maybe you have an excitation, and that excitation is, say, just a circle like that, right? This is the simplest excitation you would have. The circle up here is the simplest excitation you have. That would be the hydrogen atom. It will be an excitation which is just a circle. But you might now have a knot, like the knot that you make on your shoelaces. But in 3 dimensions, you can tie these knots. And then the next knot would be helium atom. They knew that the helium atom was the next simplest one. And therefore, more and more of sophisticated knots would represent more and more further and further atoms. So the atoms, the variety of atoms, was reduced to saying that these are just excitations in ether. And they differ from each other in their topological structure. Namely, the circle is called unknot. A circle is just the simplest knot, if you like. And then if you just make a thread, right, you can loop it around and make another more complicated knot and more complicated knot.
I see.
And then they persuaded a Scottish mathematician by name Tait, T-A-I-T, to look into this. And this is how the famous branch of knot theory in mathematics began, with these ideas. And it is a really flowering branch of mathematics now about classification of knots and everything. And so this was a fantastic idea, but it turned out that's not how nature works. And that is the beauty of science, that there can be really marvelous ideas, because this idea explains the variety of atoms. This idea explains stability of atoms, because if you got one knot, there's no way without cutting it to convert it to another knot. And then cutting would cost too much energy, and therefore the atoms are stable. So this is the idea up here. And so all kinds of things could be explained. And then the spectra of atom were really about vibrations of these knots in ether and so on. But
Yeah.
just because the ideas are so attractive does not mean that they are born out in nature. And this idea, so attractive as it is completely forgotten. And then the second idea, which was Wheeler's idea, that namely it may be chemistry of geometry, is not forgotten, but on the other hand, it is not a mainstream research. And this is one part, for example, in which it is important to realize this, keep this history in mind, because there are too many claims about theory of everything these days, particularly in connection with string theory and so on and so forth. And just because mathematically something seems compelling to some people, because it's aesthetic judgment after all, does not mean that nature has to be realized. And as Feynman used to say, it does not matter how beautiful your idea seems to you. It does not matter what your name is. If it is experimentally shown to be wrong, then it is wrong. It doesn't matter. And so I think this is something that we have to keep in mind. Okay, so this is chemistry of geometry. Mm-hmm. And now I can go to perhaps what loop quantum gravity has to say about unification of general relativity and the quantum mechanics. But if you would like to discuss something else, that's fine with me also.
Yeah, no, thank you for that explanation, and especially the historical exposition. It's interesting, the concept of the ether, just because looking into it, Tesla what seemed to be a believer in the ether, and looking into, and I know, like you said, the spirit of science is revise and reinterpret when the data says to do so. And so if the model doesn't match with reality, then we move forward. But it is a fascinating topic, the ether, and how it has evolved. Looking into Tesla's theory of gravity, so that he was supposedly never able to really release, or however, all I know is that it was founded on this notion of the ether, and that there was this life force that and it seems beautiful in its description of reality, and it almost seems Vedic in a sense to a certain degree, but it doesn't make it true, like you just said. Just like the Bohr, you mentioned Niels Bohr a second ago. In school, in high school, which is my highest level of education, I learned about the Bohr model of the atom, and I also learned about the Vesper model of the atom, the valence shell with the orbitals being probabilistic and they're not determined, and how that now I see relation to quantum mechanics. And so I just wanted to point out to those that are listening that it's important, like you said, to look at the history, but to know that we used to think of these as billiard balls, these fundamental particles and things, and now we think of them as probabilities of potential places they could be once observed, if observed. And so moving forward from that conception, the loop quantum gravity and its attempt at this endeavor is what your work centers around. So I'd be more than happy for you to go ahead and on with that. Thank you.
Yeah. So loop quantum gravity then tries to face this challenge head on. I mean, it doesn't try to say that, and that is why it's background independent. So let me just say that a little bit before. Coming from quantum field theory, particle physics people often had approaches to quantum gravity in which they said that the physical space-time is a metric G, which is G mu nu, as is written in this place up here. That's supposed to be the metric. The metric is a fundamental field in general relativity. It is curved. Its geometry, curved geometry is encoded in this metric up here. If the space-time were flat geometry, then this metric is supposed to be Minkowski metric. It's supposed to be just flat. So it is really the four-dimensional generalization of the XY plane, if you like. X direction, Y direction. Now you've got G and T. We've got four-dimensional plane. So it is just flat up here in Minkowski space. So what they assumed was that they could just take the physical tensor G mu nu and subtract it from it, the flat tensor. So just introduced by fictitious background, that is the background dependence, and then quote unquote quantize only the difference between the two. Now that goes completely against spirit of general relativity, because physically there is no such thing as a flat background metric. All we have is the physical metric. I mean, this flat background, this stage is your fiction of your imagination. You can do it, but it cannot have fundamental physical significance, basically. So in loop quantum gravity is background independent. So it does not have auxiliary fields or auxiliary mathematical structures on it. It just has a physical fields of itself. And what it focuses on is really trying to construct a quantum description of the geometry. Now, how do you do it? Well, the geometry that Einstein used is called Riemannian geometry, because it was formalized and developed by Riemann in his habilitation dissertation in 1854 in Göttingen. And at that time, actually, Riemann, it was a mathematical construction, and said that, are these manifolds useful in terms of nature? And he gave two examples as where it may be useful. And one of the examples was supposed to be, in fact, space. He says, maybe space is curved. Maybe we just assume it is flat, but maybe it is curved. And the second example he gave, by the way, was there's a three-dimensional space of perceived colors, human colors. And amazingly, it is Newton who figured this out, that the space of human perceived colors is three-dimensional. And it has really a manifold structure. It's not a plane. It has a complicated conical structure. And Riemann said that space would have a metric which would measure distances between how far the two colors are in human perception and not. Okay, so general relativity is based on the geometry which is introduced by Riemann, and that is a branch of analysis which is, if you like, more advanced calculus. So it's really mixing geometry, as is taught in high school, with calculus. That gives us what is called differential geometry, and that differential geometry is what Riemann used, and that particular one is called Riemannian geometry. So it's a mixture of calculus and geometry. So Einstein, every new physical theory needs a mathematical syntax. Now, why this is so is a really fascinating mystery.
Yeah, that is.
But Newton needed calculus, right? Without calculus, that could not have been developed, and he introduced that from first principle. So here it was this Riemannian geometry, and now the question is, what replaces the Riemannian geometry? If you want to do, will take into account the atomic structure or the quantum structure of the geometry. So what we did systematically in the 1990s, I started this project, but there are many people who worked on it, is to really develop a quantum theory of geometry, of Riemannian geometry. So it's a very detailed mathematical theory. It's well defined. There are no infinities. In quantum field theories, there are often infinities which are smuggled, and then you have to remove them by hand. This is really mathematically very well defined, very sharp thing. And now, in this geometry, then, in this quantum Riemannian geometry, using them, you can ask, how are you going to describe geometrical observables? For example, in front of you, there is a screen, and that's a two-dimensional surface. And that two-dimensional surface has an area. In classical geometry, to assign to it an area. If it's flat geometry, it's just length times the breadth, right? And the width. The product of the two will be just the area. But now, anytime, like, for example, in an atom, like an hydrogen atom, where I got observables like energy, like angular momentum. And classically, these observables take continuous values. You can change the energy continuously. You can change the angular momentum continuously. But quantum mechanically, they become discrete. And that is what we mean by saying they're quantized. Technically, one says that you have observables represented by some operators in quantum mechanics. And these are the non-commuting operators that Heisenberg had used, for example, introduced us to begin with. And these values that you measure are eigenvalues of these operators. So that is a technical term. And so the statement is that quantum mechanically, it emerges immediately when you have represented observables using the mathematics of quantum mechanics. It emerges that many of them take on only discrete values. And that is what happened with the hydrogen atom, energy and angular momentum. And that is why we say energy is quantized, angular momentum is quantized. So what we found was that when you do the same thing, that observable, like the area of this thing, is actually quantized. It's actually discrete. It cannot really be changed continuously. Now you might say, well, why not? I mean, I can just, for example, I'm weaving a scarf, for example, or a sweater, and I can just add another row to it, and I can change it continuously, right? But I mean, when you think about it, you're not changing it continuously, because between the threads there is some, if I look at this shirt up here, or your t-shirt up here, and I look at it under the magnifying glass, I see it is owned by threads.
Yeah.
So it is not really being changed continuously, but for our eyes, it is a continuous object. The screen looks continuous to eyes, but it's not continuous. The atoms, of course, to change the area, I'll have to remove one atom to decrease it, or to increase it, I have to add one atom. So there is the smallest area I can add and I can subtract. There is the smallest area I can add to my shirt, or I can subtract to my shirt, because I just have to have another thread. Another thread will change it by quantum area, if you like. So this is an analogy, but this is exactly what we find. And this is something from first principle. This is not put by hand. One just finds that the areas, and also geometrical observables like volume, but area technically turns out to be the most interesting, most important one in the whole subject. These are quantized. And therefore, the statement is the following, just as I already talked about my shirt. My shirt looks at like a continuum, but on the other hand, it is not a continuum. It really is discrete. It is owned by threads. And for all practical purposes, I can use it as a continuum, but at a fundamental level, it is not. And so the same is true with space, with the geometry of space itself. The space is really, geometry of space is woven by quantum threads. And these quantum threads are excitations of geometry itself. Just as, if you like, photons are excitations of electromagnetic field, these quantum threads are excitations of geometry itself. But they are polymer-like. They are one-dimensional. They are not punctual, but they are really polymer-like. They are one-dimensional. And they in the normal, like for this, in the normal world, if I just take a piece of paper, for example, like a piece of paper here, I don't know if you see it.
Yes, kind of, yeah.
Kind of. So if you take a piece of paper, it looks like it's all continuum, and I can change the area continuously, but it's not the case. And the statement is that it really is one-dimensional fibers up here, one-dimensional is crisscrossed by one-dimensional excitation of geometry, and they are so densely packed that for our practical purposes, we cannot see the discrete structure. And one can say, oh, wait a minute, but I make this experiment in CERN, in high energy physics, and so on and so forth. And there I can go to very, very high energies. So I can go to minute distances with the elementary particles. Why can't I see this discreteness? Well, the reason is because same as what Wheeler was giving before, namely those elementary particles are still gigantic compared to the scale. So you don't have energies, or you don't have fine resolution in the accelerators that we have got to see this structure. You would need 10 to the 20 times more resolution. It's completely out of question about building such things on Earth. And so, one is led to it by saying that gravitational field is a physical entity, but it is encoded in the geometry of space-time. Geometry of space-time in general relativity is described by Riemannian geometry. Therefore, in quantum mechanics, we need quantum Riemannian geometry. You take these three things together, and you find that there is a discrete spectrum, there's a fundamental discreteness, and space-time continuum is woven by this quantum threads. And now the question is that, well, if we're not going to be able to see this here, where are we going to be able to see it? And then the statement is that one would be able to see that only in the extreme regimes in the universe, and that would be near the Big Bang and inside the black holes. So that is when loop quantum gravity would come on its own. It does not, it always has corrections. Just as you can use quantum mechanics to solve the detailed equation to describe how your car is moving. It's a waste of time, because the 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 correction that you will get, the quantum correction you will get to classical motion is completely, totally negligible. You will never be able to see that deviation. The same thing is true here. General relativity is an excellent approximation under not only normal circumstances, but even near the black hole horizons, near the horizon of the black hole, not in the black hole singularity, but near the horizon of the black hole. The curvature is still much, much, much smaller, 10 to the minus 65 times smaller than that would be needed for quantum gravity corrections to be really important up here. So you really have to know what happens at these singularities, at these extreme cases, to really get predictions. And a lot of work in loop quantum gravity has focused particularly on cosmology. It's called loop quantum cosmology. And one is trying to get, I mean, more than now 15 years, people have worked systematically on it to make predictions. First of all, to say that, well, does this picture of quantum geometry, of there being atoms of geometry, which come on their own, if you like, under normal conditions, the space-time is a continuum. It's like a fabric. But near the Big Bang, where the curvature is so large, this fabric gets torn apart. And once it gets torn apart, you have to really use the fundamental threads. There is no longer a continuum fabric, but you have to look at the atomic structure and see what happens to this atomic structure. But if you do that, it may be that you will get a contradiction with observations today. That's the beauty of experiments, right? I mean, or physics, that some small things can have large effects up here. And so what has been shown is that no, this does not happen. It is all compatible with observations. And furthermore, one can actually explain certain anomalies in the cosmic microwave background using loop quantum cosmology. So this is an ongoing, very active area of research. It intertwines with observations, and I'm taking Feynman's quote very seriously, that you cannot build a theory in a lofty vacuum. But even if it is difficult and so on and so forth, we have to try to make contact with observations, and this is what is being done. So this is my brief summary of where we are in loop quantum gravity.
Excellent. No, thank you. I think the description was one of the best I've heard for likely the reason is that you being one of the pioneers of it, but the description that you provided, I think it helps conceptualize what the goal of this is, which is to find something that this ultimately is subservient to a grander theory, which is quantum Riemannian geometry, and that this geometry itself is what gives rise to what we call space-time, or it's a physical, gravity becomes a physical construct relative to this geometry. And you mentioned there black holes, singularities, and all of those things, and the cosmic microwave background, all of incredibly really interesting aspects of cosmology in general for someone, especially like myself, who just glances over these things and they just seem very peculiar and interesting. And I guess when I think about the cosmic microwave background, if you don't mind me asking about it in this context, is early universe evolution. It's so, in my understanding of the cosmic microwave background is that it shows areas of higher densities where maybe galaxies may have began to coalesce in the early universe, and this light has been stretched out over time into microwaves, leaving behind somewhat of a blueprint of the early universe. At what point, and how does the strong, weak nuclear forces that are, I guess, came into existence prior to electromagnetism and gravity, where are those forces predicted by the mathematical equations of loop quantum gravity? I mean, I find the nature of these fundamental forces and the cosmic microwave background, the strong and weak nuclear forces are so fundamental to most people's conception of what holds the nucleus together. What is it that brings multiplicity out of the unity, kind of? And I based on my understanding.
So now there's several things you said. I got you.
Okay, I wanted to make sure that it didn't sound that it was coherent at minimum.
Right. So, but there's something that you're not correct. So let me just say a few
Thank
things.
you.
I mean, I understand the general topic, but let me just say.
Thank you.
So the point is that the cosmic microwave background is really very, very early. It is when universe, quote unquote, is only about 300,000 years young. Okay. Anything like galaxies and first stars and so on, they came much, much later. So cosmic microwave background has nothing to do with first galaxies and forces between them or anything like that.
Okay.
That's the first thing. Okay. So what is it that we know? Now, it was assumed that there is a Big Bang normally, and the universe began with the Big Bang according to Einstein's theory of general relativity. But modern cosmologists don't think of Big Bang in the sense of an initial singularity. This is really important. There is a very nice video. It's only about 20 minutes long. It's not very long. It's only about 20 minutes long, and it features 7 of us. I mean, there's Roger Penrose, there's Stephen Hawking, there's Alan Guth, and some other people. And it is called something about the new meaning of the Big Bang, it's called. And it is worth watching because it's very short. And you'll see that these people came together from completely different backgrounds, completely different approaches to quantum gravity, to cosmology, etc. And they all had exactly the same thing to say, that when modern cosmologists talk about Big Bang or Earth, they're talking about an early hot phase of the universe, and not at all the beginning of the universe, and not at all the singularity of general relativity. So let me just get that out of the way, because there's a confusion in the terminology very often when people talk about Big Bang. So the idea is that there's an assumption that there was an early phase of the universe, which was very, very hot. But the point is that one can go before that phase of the universe. So if you like, the Big Bang, in this case, the hot phase of the universe came afterwards. I mean, we know what happened before. And it's one of the 3 scenarios, but it is most widely used, inflationary scenario. What happened before was inflation. And so the statement was that basically you look at the end of inflation, and between the end of inflation and at that time, it is at the end of inflation that somehow the basic elementary particles that we know today came into beginning. Gravity was always there. Laws of nature was always there. It is not something that is evolutionary, but there wasn't matter before that. I mean, what was there was really, in the inflation scenario, there is just a scalar field or bunch of scalar fields up here, which are rolling down a potential. The details are not important, but the important thing is that basically that the matter that we know about today, which is called the standard model matter of particle physics, that came into existence through at the end of inflation, the so-called reheating phase. Then the universe got hot, and then this, and the statement is that all of the laws are always there. I mean, in this analysis, one is just using general relativity, not quantum gravity, because this is already in a phase in which the curvature is very small. Quantum gravity effects that I talked about before, loop quantum gravity effect, that even before that, even before inflation, what happened. So let's not talk about that. Let's just stick to the point that you were raising up here. So cosmic microwave background is the following. So there's end of inflation, then the elementary zoo of elementary particles that we know it's supposed to be born. These are frontier areas. It's not that this is a final picture at all. Even inflation may go away or something, but this is the tentative picture. And the beautiful thing about science is always that one is not ashamed of tentative pictures. That's how we make progress in the frontier of science. There's a competition of ideas. Some ideas survive and some don't. And everything is finally decided by the observations and experiments. Okay, so at the end of inflation, there was reheating. That is when the zoo of elementary particles that we know talk about. But then the universe was very hot, and since it was so hot, there was a dense, this is what people call Big Bang in the new sense of the word, this hot phase of the universe, that the things where light could not escape. I mean, there was just interaction that was happening between everything else, between everything. I mean, it was like a plasma. It was like a soup of all the things together. So, and then the statement is that as the universe cooled, and this is about 380,000 years afterwards, when the universe cooled, then it became possible for the plasma to condense into atoms. In other words, the hydrogen and the protons and the electrons could actually bind together. Before that, the universe was so hot that if the electron tried to bind together, it would be blown off in no time at all. Because there's so much energy that is impinging on it. There are so many photons and so on, so they could not bond. Okay. So the temperature was sufficient here, has dropped sufficiently that atoms could form. And once the atom could form, then the photons could escape. And that is why the surface of cosmic microwave background is often called the surface of last scattering, because that is when the photons escaped. They were always interacting before that, in this plasma. Then they could become free and they could propagate. And now we see that. So that is what the cosmic microwave background is. So cosmic microwave background doesn't really tell us too much about what happened before this this decoupling between photons and the atoms happened, and the photons started propagating.
Okay, understood. Yeah, I think my misunderstanding there on the cosmic microwave background. I think before I thought potentially that it was like a map almost of the early dense areas of the universe. So thank you for the clarifying. It's this new model of looking at the Big Bang. The video you mentioned, I'll have to certainly make sure to watch, just because we do, or I do, tend to think of the Big Bang as this singularity of sorts. I mean, that's what it's assumed to be. So thank you for the clarification. And also I hope to learn more on the cosmic microwave background. I think that it seems like something that will potentially have a lot more to offer to your field of cosmology potentially in the future, just because it's so unique. It's a unique thing.
Right. So let me just say something so the idea is that this cosmic microwave background, at that time, there are seeds. In other words, in this cosmic microwave background is not completely homogeneous. It's almost the same temperature, almost homogeneous everywhere, but not completely homogeneous. There are inhomogeneities, or there are anisotropies, which are 1 part in 10 to the 4, 1 part in 10,000. And so there are slightly over dense regions and slightly under dense regions. Now, under gravity, anytime there is slightly over dense, attracts more, because gravity is attractive. A region which is under dense, the matter flows out of that under dense region towards the over dense region. As they say, rich get richer, and poor get poorer. Yes. So this is what happens up there. And then the thing is that if you just look at the cosmic microwave background and then go forward in time, then the known astrophysics, gastrophysics, nuclear physics is sufficient to tell us that the large scale of the structure of the universe that we see today came out of these seeds. So these are good seeds for the cosmic microwave background.
I gotcha. Okay. All righty. Well, that makes sense.
So the seeds in the microwave background the inhomogeneous in the microwave background are good seeds that produce the large scale structure of the universe under known laws today.
Thank you. Thank you for the clarification. I basically the prior existence of these laws is fundamental to the idea that these laws pre-existed even the geometry that we're referring to when we're talking about the Riemannian geometry that describe. Okay, understood. And to move on, we talked about earlier the inner world, the outer world. We just covered. You just brilliantly laid out the outer world for us, where it's at and what the history of it is in a concise manner. I think that was an excellent synopsis of as quick as you can on something like that. So thank you. And the inner world, the way I've been looking into it, that struck me as my avenue of amateur research. And as I've gone into this, you mentioned Hoffman, Dr. Hoffman earlier, a very interesting character. I enjoyed my conversation with him, and he has this tagline, if you don't mind me quoting him briefly, that space-time is doomed. And it's become a tagline of his, and he explicated it very well to me, but of course it's a hard narrative to get into, to really conceptualize. What he means by that, I assume, and what he explained to me is that consciousness is ultimately fundamental. When we talk about the inner world, I see it as our ability to feel qualities of experience. Do you mind elaborating on Donald Hoffman's theory and kind of your definition of the inner world?
I cannot elaborate on.
Oh, not
Hoffman's theory. I
elaborate
only
on it.
got
I'm
one.
sorry. I meant like kind of give your opinion on what the consciousness as a fundamental entity would mean.
Right. Now, there are several things that are said. I mean, I read a few things that he had written in articles and such things, and I feel that the views of consciousness, that somehow the fact that what we call reality is not the objective reality, it is a reconstructed reality, and evolution has had a huge role to play in it. These are some of the themes that he says, and I completely agree with that. I mean, that's absolutely true. And it's also, I think, another neuro. I do not know Professor Hoffman at all, but I do know Professor Carl Friston that you also had interviewed, I think, and he has a very very persuasive models about how perception actually takes place. That we actually have models in our head, if you like, and then we get the sensory data, and then there's a fitting between which model agrees with the sensory data the best, and then we think of that as being the reality. That is what I perceived. That is what happened. That is what I saw. But I mean, different people might have different models, therefore, and their fitting might be different, and that is why there can be differences about what actually happened. So I'm very more than sympathetic to this view that what is normally called reality is really reconstructed. And then this experiments on split brain that were done, I don't know, in the 60s, 70s, and 50 years ago, they bring this out very, very clearly that we make up a story. We create a story about what the reality is. So this part, I'm on the same wavelength. Okay. The
Understood.
other part, I don't agree, and it is because I think that one just somehow maybe that is a key point to many people to look at the reality. And this is also the case in the spiritual world. They always talk about the absolute reality, the absolute truth. And the point is that, I mean, as we saw just now, there are models of reality. And I mean, is there reality by itself, or is it just an abstract limiting point in mathematical sense? I'm agnostic about that.
Yeah.
Most science assumes that there is actually an external reality, or it could be internal. I'm not sure. There is actually reality that we are trying to converge on. And from that point of view, what we have are constructs. And these constructs, concepts, frameworks are the best fits to our perceptions, to our experiences. And space-time is an excellent, excellent fit. It doesn't mean it is real, just like Newton's space-time was not real. I mean, if you believe in Einstein's space-time today, then Newton's space-time was not real. It's not a stage, it's not existing forever, etc., etc. It's a dynamical entity, it's not permanent, it is affecting, it is geometry changing and such thing. And if you bring into account quantum theory and something like loop quantum gravity does turn out to be completely right, then even Einstein is not right. So we don't have the space-time. I mean, space-time is a concept, and I think it's just not useful, in my view, to think about is absolutely real or absolutely not real. I mean, I don't know what is absolutely real at all, right? I mean, maybe at that level, I do know that if you like, I mean, I have perceptions, but I also know that I recreated these models in my head, so that is where I would disagree. That space-time is
doomed.
I mean, doomed. Yeah, that viewpoint I agree. I mean, space-time was never, in my view, absolute reality. Space-time is an excellent conceptual framework to explain our experiences, and we have made them more and more sophisticated as we go on. Now, he also talks about quantum mechanics. Sometimes he talks about quantum mechanics saying that there is no reality to particles or something. And again, the statement is that particles and waves, these are classical concepts that we are trying to use in order to create a story around actual observations. But we very well know that there is not a single observation that actually has violated quantum mechanics. And so therefore, there is a coherence to it. And that, so the statement is that that coherence refers to description of the external world in terms of these equations. And what is limited is really using words. I mean, just like in quantum mechanics, also general relativity, we use words. In general relativity, you call about gravitational field. But I mean, Newton told us that there is no such thing. I mean, Einstein told us that there is no such thing as gravitational field. There's only space-time curvature. It's just useful to talk about some concepts. So similarly, it's useful to talk about, in the internal world, it's useful to talk about some certain concept, but one should not take them as being absolute and being doomed, etc. Yes, I mean, I completely agree that even Einstein's view of space-time is far from being unchallenged. I mean, far from the final one. It is going to evolve, it's going to change, it's going to. So my point is basically that it's not that fruitful to talk about anything like, being doomed, because I think what we have is really notions, and all notions are doomed in some sense, because there will be better notions because they have limitations up here. So that is my sort of. I mean, it's a very interesting question. I don't have any opinion about it.
Thanks.
Feynman himself wrestled on it, about the question about whether there is actually reality, or he called it like an onion. He says we peel onion and then there's another layer. We peel onion, there's another layer. Are there going to be layers? In other words, are we going to have better and better and better and better models or not? Now, the place where I have something slightly new to say is that there is external world and there is internal world. And neither of them gives us a complete picture. For the sake of argument, let me just say that there is some reality. Okay, it's either external or internal, doesn't matter. There is some reality up here. It could be a limiting concept, I do not know. I'm agnostic about that. But the point is that what we are doing is we're trying to give a description of it in patches. Now, for this notion that was introduced by the Riemannian geometry, is very useful. And if you take, for example, a plane, like the screen that you're seeing, but look at it, infinite plane, then any point on it, I can coordinatize it by X and Y coordinates. So X and Y, two numbers suffice to describe the whole plane. I'm trying to think of this plane as being reality, substitute, a poor substitute for reality. Okay, and then the statement is that in this case, two numbers suffice. So there will be a final theory. There will be some theory, some concepts that will cover this reality. But on the other hand, if I think of it as a two-dimensional sphere, like the Earth, the surface of the Earth up here, two-dimensional sphere, it cannot be coordinatized. You cannot label each point just with two numbers. What you can do is you can cover the northern hemisphere and almost everything except the southern, the South Pole by one coordinate system. This is a mathematical fact. Or I can do everything except the northern hemisphere by one coordinate system, but two numbers, basically, every point. But something will always I'll miss out. One coordinate system will cover everything except this North Pole, and the other one, everything except the South Pole. Of course, this is the simplest model of manifold. General models of manifold, you really have to have patches. In other words, there is some smooth structure, and I just cover it with patches. And the important thing is that wherever there is overlap, there has to be consistency. And so this consistency between one patch is one coordinate system, is like one description of that manifold, of that region of the manifold. There's another description. So, but the two things are actually overlapping with each other. They're not, So in this way, they're not overlapping with each other. If you see my hands.
Yes, yes.
Yeah, in this way, you are not overlapping each other. But if they are overlapping with each other,
Yes.
then
Yeah.
there is this region in between up here. In that region, I got two descriptions, one from one patch, one from another patch. And there has to be consistency between them. And this is what I think is, my view, the fundamental problem of the inner world and the outer world. Namely, I don't think either of them covers the entire reality. And I think the challenge for us is to understand what they cover, and then to see where the overlap is. And then in that overlap, if in fact the descriptions are consistent, the descriptions are coherent.
No, I understand what you're saying. In fact, it's interesting. It's almost observer dependent in order to put together this description, and that observer dependency that's relied upon to construct what we would like to call the subjective realm of reality. Sometimes it seems to me like, I think you made this distinction in what you just said, is that when you're looking for this objective reality, it almost muddles it up a little bit, because then you're looking for something that may not be independent of observer, which we already kind of know. It seems to me that things generally aren't observer independent, and so. And that overlap, that Venn diagram looking structure you just formulated there with your hands, is, it seems to me like the act of perceiving the external world, interpreting it, and then encapsulating that experience with language is the process of coalescing the inner and the outer. And that's a fundamentally mysterious connection. And so I was thinking a lot about, you mentioned Carl Friston. Carl Friston's done a lot of work with schizophrenic patients, and his work with them goes to this notion that schizophrenia potentially is the inability to properly formulate what should be your generalized template, so to speak, for reality. So you expect this in your day-to-day environment. In the free energy principle dictates that surprise be limited. And as we limit surprise, we have a more basically inline subjective and outer together. And that makes for an easier, more predictable life. And we can probably all agree that it certainly does. And touching on Carl Friston specifically there, it seems to me like it's critical that it's shown with schizophrenia that if your inner reality is somehow misaligned with external reality, things can go awry quickly. So we know that it has, right? I mean, with the notion of that, perception is dependent upon, and if you perceive incorrectly, you can have a totally different view of reality. Just like time being subjective. And it's almost like causality at its core is what's most fundamental to a certain extent. But on this note, it does seem to me like that Carl Friston's work does hint at what you just said, that there has to be this kind of overlapping kind of connection. And that was just my recapitulation of what you were saying that I thought was neat between Carl Friston's work and what you just said, that maybe those kind of synergize with each other. Another gentleman that I have found extremely, obviously, I mean, one of the most gifted physicists in the world, Roger Penrose. He has spoken about you in the past and said wonderful things, and I've really tried my best to understand his work. I'm not very good at understanding his work, but his model is a quantum kind of based wave collapse model. Anyways, I find it a noble attempt to take his specialty and put it to use in the consciousness field. And of course, it's known as Orch-OR, and it involves work with an anesthesiologist and the combination of the two and all of that. So what do you think? Okay, sorry. Yeah, what do you think about the work he's doing with the kind of, is it really a bridge building between the two he's doing, or is he trying to subsume them into each other? And do you think his work has anything to teach us about this combination?
I know Roger's work very well. I mean, I was Roger's postdoc, and then for 20 years he has been distinguished visiting professor in the institute that I built, and he visited us every year. I discussed at length a lot of these things, even actually. Yeah, so even 30 years ago, when these first ideas were discussed in 1990s, I think, or even before, actually, I remember in '86 in Santa Barbara, we had a lot of discussions on this issue. Okay, so first of all, what is idea? And then secondly, it's work with microtubules and then the current status. So the idea is actually something that Roger proposed, and Roger is always very, very generous and very very proper about these things. That this idea was very similar to the idea that GOC had proposed some time ago. So sometimes it's called GOC Penrose idea of the spontaneous collapse. And I know both. I mean, I know Roger much, much better than GOC. I also know GOC. I corresponded with them and so on. So I think these are all fascinating ideas. So what they want to say is that the following, that in quantum mechanics, there is actually a problem. And the problem has to do with and there's a unitary evolution normally, and then measurement occurs. And when the measurement occurs, the wave function is supposed to collapse. And only one of the outcomes. Until the measurement, the probability that the result could be this, that, or the other, and then you make the measurement and the result is just one. So that is called the collapse of the wave function. And what the question is that, this collapse of the wave function is a very mysterious and I think unsatisfactory part of the quantum mechanics. It has many, many issues. We should not go into all of them today.
Yeah.
But the thing is that what GOC had proposed was that maybe there is actually a spontaneous collapse that occurs. And he was proposing some mechanism. And Roger proposed that this mechanism has something to do with space-time geometry. Namely, if I got, for example, two masses, which are sitting up here, and then if I prepare a quantum state in which the probability is that the mass is here is 1/2, and the mass is here is 1/2, supposing I construct such a quantum state, then its gravitational field would also be have a strong gravitational probability of having a strong gravitational field here and a strong gravitational field here, right? And in between, the gravitational field will be low. Is this part clear? Maybe I can start from scratch. Supposing I just have one blob of matter up here, then the gravitational field near the blob of, in this region of blob of matter would be strong, and away from the blob of matter would be weak. Okay, because near the blob of matter it will be strong. Now, supposing I prepare a quantum state in which I don't have a blob of matter which is sitting here like classically, but there's a probability that the blob of matter is sitting here, and there's a probability that the blob of matter is sitting here. Okay, namely 1/2, 1/2 probability.
Yeah, the Schrodinger's cat, but in subatomic level. Cat, exactly. Yeah. Okay.
Or even at not subatomic, even macroscopic level. I construct something which is so for a thought experiment, we can just consider even a billiard ball. I somehow put a billiard ball in a superposition state. Don't ask me how. To do it properly, one would have to use something subatomic. So if I had such a quantum state, 1/2 here and probability is 1/2 here and 1/2 here, then the gravitational field will have probability to be large, half a probability that is large here and half a probability that is large here, right? And in between is going to be small. But now supposing you actually come and make a measurement of this blob of matter and find that it's here. If it is here, then suddenly the probability here has gone to 0. And therefore, the geometry would change dramatically suddenly here. Okay? And the idea was that space-time geometry, this is a principle that Roger wanted to use, that the space-time geometry cannot be too superposed. Somehow, just putting it by hand, somehow classical space-time geometries are preferred or something. A little bit of quantum superposition is okay, but if it is too superposed, then there is a spontaneous collapse, and either this geometry is peaked here or geometry is peaked here. Suddenly, spontaneously it happens. There's no mechanism. This is a law of nature, some fundamental thing that will ultimately be explained, but he's just postulating that. So that is his postulate. This happened a long time ago, actually, and I was very, very interested. Roger used to visit us very often. We had a lot of this thing. So as a side remark, and this is completely side remark, it's not too relevant, I did a calculation that long time ago with the ideas that Roger had then, which have evolved quite a bit. an idea. And the idea was that, well, I looked up literature. This was again in the 90s, early 90s, so it is more than 30 years ago, so I don't remember the details.
Yeah.
I probably had notes somewhere. And I consulted all my biophysics colleagues and so on and so forth about, human retina. How many photons do you need so that you actually register something?
Uh-huh.
And I looked at that. And then I said that supposing this much energy went into the eyeball, then I suddenly see something, right? So then, it's called, then what triggering happens? How much, when the current goes through, how many chemicals are actually released in the neurons, the whole thing. And I did, this is of course very rough calculations because what is available in biological literature. I found that, and I found that it was not enough. In other words, the gravitational collapse would not occur.
Oh, wow.
So therefore, I found at that time that in fact, there are these perceptions. Everything cannot be reduced to this idea of spontaneous collapse. Now, this is very rough back of the envelope calculation. It's not back of the envelope. It's 2 or 3 pages calculation, but not a sophisticated calculation at all. In the sense of took the best data that my colleagues gave me. And
Certainly,
that's what I did.
certainly, because I was wondering where what the threshold was for the you mentioned the quantity of photons required to elicit a perception that is, I guess, intelligible to the. It's very.
So it was all written down.
That is very neat, though. Oh no, of course, yeah. I was just. I think it's very.
Literature.
I think it's a very fascinating, way of going at this. That's like that's what I'm getting at. Not necessarily the number, but just the fact that you came to that model of this is what we need to figure out for this to be is something I've always looked into this theory, and of course I'm limited in my understanding of it, but that is a very neat, unique way of coming at it. So I just find that cool.
Right. But then since then, as you know, in the last 20 years, since Hammeroff and Penrose proposed this microtubule mechanism, there have been many, many investigations in neuroscience. I'm not a neuroscientist, so I cannot really. There are some physics papers which I sort of roughly understand. I'd say roughly because, again, even these physics papers use some facts about chemicals in the microtubules, which I'm not very, even the crystalline structures and such things, which I'm not so familiar with. I just have to take their word for granted. And the general consensus in the neuroscience community, as you probably know, is that no, somehow the brain is too wet and too hot.
Yep.
Also, that to have such mechanisms is something that you perhaps are useful for quantum computing, but in the brain, decoherence would occur very quickly, and these things will just not be. The quantum mechanics is not relevant, and microtubules are not relevant. And then Hammeroff has written back, and there is a back and forth conversation on that. But just recently, like in this year, 2022, there was an experiment in Gran Sasso in Italy. And the interesting thing is that this experiment was done, this is a completely physics experiment, but this experiment was done by very leading experimentalists who work in Gran Sasso. There's this cave in Italy and the underground experiment up here, not cave, underground experiment. And but DOC collaborated with them, Rogers. And at the moment, the conclusion is that the spontaneous gravitationally induced collapse is I don't want to say is ruled out, but it's very, very unlikely.
Yeah.
And this is an experiment in which they just use physics things, right? In other words, it's not. So what they're using from microtubules is just the number, the scales on which when this collapse should occur. And then they conclude that this collapse does not occur on the scales that is needed in the microtubules. So you can read up about this. These are Gran Sasso experiments that have been done. So to me, that is kind of conclusion. Now, as I said before, right? Extremely good people like Maxwell and Kelvin had these great ideas about atoms, and they did not turn out to be right. To me, it's almost. Of course, it matters a lot for what happens to science later, but in terms of imagination, in terms of beauty and value of their idea, at the time it was proposed, the fact that it turned out to be wrong does not take anything away from it. So similarly here, what Roger and DOC and people are proposing are really very interesting ideas, and they may be wrong, but that's not the point. I mean, of course, if they're right or they're wrong is important for the future of science.
Sure.
But as a value in the in-between stage, they're extremely valuable. There are also works by Jerome Martin, who is a astrophysicist, cosmologist in Paris, in the Institute of Astrophysics in Paris, who has done work on cosmic microwave background and also offered some evidence against spontaneous gravitational collapse.
Oh, wow.
So this
That's
is
fascinating.
another thing that, but I mean, this is an ongoing debate. So to ask me for my view is that I think that such bold ideas are needed. I think the evidence currently doesn't favor them, but is not conclusively ruled out. The neuroscience people don't take it seriously at all, and I don't think it's because of the idea is wrong, but that spontaneous gravitational collapse could be responsible
Certainly.
for things in process of the brain is what they're complaining about, and so I think this is an ongoing thing.
Yeah, no, yeah. Thank you for pointing out the recent research that was done kind of on that. And I think I was under the same understanding, at least as far as the physics of the nature of the spontaneous collapse was something that certainly might be, overturned as far as the proof is concerned. However, like you mentioned, the neuroscience aspect of it. If you don't mind, I wanted to run something by you, some of my thoughts on the biology, specifically the biology of the microtubule. When I look into consciousness, the work with anesthesia seems to be one of the few avenues you can use. And so the removal of consciousness is essentially accompanied by the paralysis of movement, lack of memory formation, the inability to attribute sensation to self and those kinds of things. I was fascinated by Hameroff's work in this part of it, because obviously there's this dipole state. There's this superpositional state in the microtubule, the fibers of it. And that is suspended. That constant dipole switching is suspended when anesthesia is administered, and that's accompanied by loss of movement. And then, of course, at the most prokaryotic, basic level of biological life, I looked into this study that was done on anesthesia administration to bacteria that are single cellular, and it actually acts the same exact way when you anesthetize a bacteria. And the bacteria is actually utilizing its flagellum, which is made up of tubulin fibers, the same thing as microtubules in regular cytoskeletal elements. And so I found it kind of interesting, at least the biology part of it, whether or not the spontaneous collapse part of it, it may be not the mechanism or the physics of it correct, but I do think that Penrose, of course, in yourself, the work that you're doing is definitely, there's people going to be standing on y'all's shoulders, later, just like science always seems to be standing on the shoulders of giants. And so these, like you said, these theories have great things to offer, but if just the physics of it's wrong, if anything, there's something to be said about the biology of what they've discovered. And so it's interesting to get down to that single cellular level and find out that, movement is really basic to consciousness when talking about anesthesia. And so, that was just my 2 cents on I think there's a uniqueness between movement, the cytoskeleton, something fundamental about how cytoskeletal components are prevalent across all of life, and this combination of an anesthesiologist and a physicist, two of the best in their fields, together has, on the side of consciousness, coupled with your work and everything, I think it's pretty cool, regardless of whether or not
I don't think I contributed to this at all. I mean, other than listening and so on. But I agree that this is really cool work. I think that there's other thing that is sort of, to me, much more fascinating. I mean, it's more fascinating for other reasons, because it goes more into the internal world rather than and that has to do with again, it is about a discovery which is about 15, 20 years. I don't know if it was discovered then, but a lot of progress has happened in the last 15, 20 years. And that has to do with the circuit in the brain, which is called default mode network, DMN. And so this is not to do with losing consciousness or not. This is always keeping consciousness. But that is a circuit which, for example, is always active in normal human being's brain, and that is a circuit which is associated with ego, with me, my, mine, and constant dialogue that goes on, even when one is by oneself, planning for future, planning for past. This is always going back and forth, and so on and so forth. All that has to do with this DMN. That is it. Now, there were experiments done at Yale, and by, I think, Brewer was the main PI, the principal investigator, and they found that in the people who had done meditation for many years, most of them from Buddhist traditions, that during the meditation phase, that actually quieten down. Right? This DMN, and there's a functional circuits that are all active, but this default mode networks itself that, and then that is also the stage in which they experience some levels of oneness with the universe, or something transcending our day-to-day consciousness. And then, surprisingly, there were some outliers, very few, but that for whom, even after they stopped meditating, the DMN was quiet.
Yeah.
So therefore, I mean, that, in other words, there is a state of bliss, if you like, or stillness, I think is how it's described.
Yeah.
In these people, and I've spoken to one of these people very much, and the stillness is always all permeating. So this is again an example of what I was saying about this overlap. I mean, this what we're talking about, Hameroff and Penrose, and it's also an example of an overlap between the internal and outer world. But there's internal world that doesn't feature as strongly, in the sense that to me, it doesn't feature as strongly as it does in this experiments in which people are doing this meditation and switching off the DMN circuits and so on. So what I'm saying is that there's a lack of consciousness. I think I take it back. I mean, it's very similar, actually. The two things are very similar. That in which there is a fascinating thing is that there is an overlap between the internal world and the external world somehow. Namely, something's happening in the microtubules, and then lack of consciousness. And here, something happening but without any anesthesia or anything, but in the brain, in circuits of brain, and then associated experiences. So the difference is that here there is an associated experience. In the other case, there is lack of experience.
That's a good point. Yeah.
And so the thing is that here what people talk about, states of enlightenment and etc., they may well be complete correlated with this internal with this switching off of this DMN completely. So that would be an example of compatibility of the two coordinate systems, the two charts that I talked about. Namely, the external world neuroscientists would say that, well, the DMN has switched off, and the internal world would say that I'm experiencing this bliss. It doesn't mean that one causes the other. It is just description of the same phenomena given in two coordinate systems. This is what I want to say. That there's it's not that there's no cause and effect here at all. So I think that is to me, it is quite fascinating that this can happen.
It is fascinating to bring the default mode network into there, because I've never put those two and two together in my mind, but I've heard it spoken of multiple times, that notion that selfhood is kind of contained, this notion, like you said, of this dual existence, to where there's me and there's the world. And I know that for a fact, like when I was studying Sam Harris, particularly, for a while, he teaches a very profound school of meditation that is in the tradition of Advaita Vedanta, non-duality. And I think there's something unique about how it's non-duality and a collapse of the dualness that comes with language and self-reference that is contained. It's fundamentally, like you just said, it's associated with the silencing of this DMN. And so that if you add that into there, it's like you almost look at consciousness potentially as the ability to reference oneself is a higher level of consciousness almost, because like you said, you can actually exist without anesthesia being administered, and you're walking around in a state of permanent enlightenment or something of that nature. And the non-dual Advaita practitioners would certainly agree that they do walk around in that state, with the inability to really attribute me as an active participant. They're more or less like there's one. And so in your studies, I know we're coming up to a couple hours, but to finish it out,
Yeah,
I was gonna ask you, just the Bhagavad Gita. I brought up Advaita Vedanta on accident coming off of your comment, but I really wanted to ask you about the Bhagavad Gita. I found it as I was looking into consciousness, and it really just opened the door for me, and it showed me how much the tradition of Advaita has to offer the world, especially their books. And I went in to read the Upanishads, and just a lot of the Indian literature touched me a lot. The people who I went to some of the temples, and I talked to some of the practitioners, and I just have a lot of appreciation for the culture, and I think it has a lot to offer the world. So, if rounding all of this out, I just wanted to ask you about the Bhagavad Gita and what you think it has for people. I think my listeners and stuff maybe have read it, but I'm always trying to talk about it. So what do you think about the Bhagavad Gita, and what has it meant to you just overall?
I think that it's sort of, I mean, it has pointed me towards deeper thinking. I mean, thinking is not word. It has pointed me towards deeper issues like that are then dealt in Vedanta. But I think it helps most in terms of how to live everyday life.
Yeah.
I mean, one of the big things about all this Eastern, particularly Indian practice, is really that it's not that you just to pursue internal world does not mean renunciation. In fact, renunciation probably is more of a hindrance to spiritual progress than that. It is more the interplay between samsara, the everyday world, the dance of lila, the graceful dance that is happening all the time, and the inner stillness. And the point is that it's not that there is inner stillness and therefore you don't act. You act. That's the point. You act. Other person may not even realize that you are in a stillness. Yeah. But you act without residue inside. And there is no, in other words, you act. There can be sorrow. There can be deep sorrow. There can be deep happiness, joy. But there's no residue. You don't dwell on it. Suffering is something that is because of dwelling. Suffering is not pain. Pain is unavoidable. Joy is unavoidable. Suffering is avoidable. Because suffering is dwelling on it. Suffering is DMN, if you like. Is really reliving, and how do I get out of it? Why am I like that? And why is the world like that to me? But how could they do it to me, etc. That is what causes suffering. And so this living in present just means that exactly, that there's pain. Yeah. So you give it to yourself to the pain. You give yourself to the joy, but then let there not be residue. This as a goal, this as a path, is something that is very good in Bhagavad Gita. I mean, there's this famous line which is quoted all the time: "Dharmanne vastuka rastu mataphaleshu kadachanam." You do your dharma. You do what is kind of appropriate, the wrong word, but do what is appropriate, but without expecting any fruits from it. Do it because it is the right thing to do, if you like, but not because it is going to lead you somewhere tomorrow and something. There's no residue, the motivation. I mean, living in present. So this is the thing that I sort of feel guidance to actual everyday living, which is very important because of what I said before, namely that this spiritual progress or spiritual endpoint or something is not withdrawing from samsara, from the everyday world, but really is seamlessly dancing with it, if you like. Namely, you are in it, you are the joy, you are the pain, but you don't have the the samskaras. You don't have the residues. You don't have the scratches on your consciousness. I think is the lesson that I find. How to live the right way, if you like.
No, that
in
yeah.
everyday life.
I think the quote that I mean, I have an English translation, obviously, and I think the quote is work without expectation of reward, which I think is exactly what you just highlighted there.
Yeah.
That concept
Yeah.
that it's so critical to our actions. And I bring up the Bhagavad Gita for that reason, because all of what we've talked about and you've explained, I appreciate your time, but ultimately it's how we live that also matters. And so I think the Vedic texts are a nice union of the two. Somehow they have a science of consciousness that's almost scarily accurate, it feels like sometimes, but then it gives you wisdom for living too. So it's nice to bring the two together, the small, the large, the contemplative, and also the neuroscientific. So I just want to say thank you for your time. It means a whole lot to me for you to have joined me today, and I very much appreciate it. So I look forward to the future of your work, and once again, thank you so much. I appreciate it.
Yeah, my pleasure. For your readers, for your listeners, for your followers, or whatever. I mean, you brought up Hoffman's thing about consciousness and so on. There are also books by, particularly one book by Robert Wright, which is Why Buddhism is True.
Oh yeah.
And that, I think, has very much lot to do with evolutionary psychology, and it makes it in a much more everyday context, puts in much more everyday context about how this evolution psychology has forms our notion of reality. I mean, this message that comes from Hoffman about that reality is reconstructed, and so that, I think, is one good place to, which bridges kind of this Eastern traditions and this current psychological not behavior evolutionary psychological ideas together. So I just thought that as you're speaking, that might be useful to your reader. Okay, thank you. It's my pleasure.
Oh yeah, thank you very much.
Good luck to you.
Thank you. You have a great rest of the day.